I'm already so terribly fucking sorry for the thumbnail and the title of this video. I seriously should wear a t-shirt with hashtag #FreshToadWalker written on it. Good morning, fellow mathematicians. Welcome back to another video. I seriously didn't think that I would have to make a video on this right here regarding my Pi Day special, but so many people were confused by this, and I seriously don't know why you guys are confused by this. I don't quite get it. So I'm going to shed a bit of light on this problem right here, why the derivative of x squared was supposedly not equal to the derivative of x plus x plus x times. In the video, well, I just differentiated this side. It led to 2 times x, naturally, and right here I differentiated term by term, so this 1 plus 1 plus 1 plus 1, but x times makes x. So 2x is equal to x. If you cancel the x on both sides, if you're a little badass, then, well, you actually get that 2 is equal to 1. Oh my goodness, boys, I'm already so terribly fucking sorry for the thumbnail and the title of this video. I seriously should wear a t-shirt with hashtag #FreshToadWalker written on it, because this, my boys and grills, is going to be fucking clickbaity. I tell you, it's going to be clickbaity as fuck. So yeah, what's the problem with this thing right here? Well, there are several problems with this problem right here. At first, I would like to define what it means for something to be added up x times. X actually being added up x times. So basically what we have is x plus dot 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 plus x, but x times, okay? But how can we write this in the sum notation, for example? Well, that would be x times the sum running from, let's say, k equals to 1 or n equals to 1 to x in this case. What do we have to write here? Well, nothing basically. This right here is what you would like to call the empty sum, for example. Explicitly, there's nothing written in here, but implicitly, we can write n to the 0th power right here, okay? And then this is going to be 1 plus 1 plus 1 plus 1, but x times. Here's the thing. Does this notation right here, this summation notation, work at the moment for a continuous variable? So, in normal case, we are only used to adding up a discrete amount of things. So, you know, adding an apple to an apple to an apple gives you 3 apples. But what does it mean, for example, to add 3.5 times to itself? Okay, so if you have 3.5 apples, what does it actually mean to add 3.5 apples 3.5 times to itself? That's quite weird. That's actually quite weird, and we're going to deal with this today. But at first, I would like to just take a look at this right here and would like to make sense of this question in a discrete mathematical way, okay? From a discrete mathematical point of view. Remember our good old friend, the difference quotient, that we can take the limit as h approaches 0, for example, and get our regular old differential right here. So we can define our differential operator as nothing but the limit as h approaches 0, for example, of, well, some function f of x plus h minus f of x over h. And you see, if you take a look at Newton's iteration method, no, not Newton's method, Euler's method, for solving differential equations, what you can actually do is just get rid of this thing right here, and let's call this right here just delta for the difference. And voila, you get the finite difference actually. So this right here is kind of the discrete mathematical equivalent to our good old differential operator up here. And why not be a little smart boy and choose our step size how we want it? For example, 1. So with 1 as the step size h, we're going to get rid of our, well, denominator down here. I'm terribly sorry. So for h being equal to 1, we actually get that our finite difference of f, let's put it that way, is nothing but f of x plus 1 minus f of x. And this formula right here works for any o. Why am I saying o all the time today? And we can just deal with all those finite valued functions right here. In a normal case, you would deal with sequences like this right here. And with this finite difference in sequences, you can actually find out if a sequence is monotonically increasing or decreasing. So we did this with the Euler-Mascheroni call. Oh no, I didn't even post this video yet. Just forget what I just said. So yeah, let's use this finite difference on our actual problem right here. And let's suppose that our x is not a continuous variable, so not element of the real numbers, but element of the positive integers of the integers in the normal case. So yeah, let's go ahead and get started. So with this, our function f of x is nothing but x squared, okay? Then we get the difference right here of x squared is nothing but, okay, this is f of x plus 1 makes x plus 1 squared minus, well, x squared. That's the binomial theorem. We are going to get, well, this is x squared plus 2x plus 1 minus x squared leaves us with, well, 2x plus 1. That's our finite difference in this case. And like I said, you can choose any h you want, any step size. And the further you decrease the step size, you are going to get closer and closer to the differential. Okay, but we also have the other side of the medal right here. So we are going to get, okay, this right here is our function, you could say, the thing that we actually want to do. So if we have f of x plus 1, that means we are going to add x plus 1 times to itself. So this is x plus 1 plus x plus 1 plus dot 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 plus x plus 1. Okay? And this x plus 1 times, meaning if we let this out of the way, this is x plus 1 added to itself x times. Okay, just for clarification purposes. But also we have this other side, minus x added to itself x times. Minus x minus dot 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 minus x. And this x times. And now you see why I've put it that way. We have x times right here, and we can subtract x times from it. So this and that and this and that is going to cancel out, and what we are left with is x plus 1 plus 1 plus 1 plus 1, but this 1 x times actually. So we are going to get, this is nothing but x plus 1 plus 1 plus 1 plus dot 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 plus 1, this right here x times, and well, this is going to give us x. Exactly, so this is x plus 1 plus x is nothing but 2 times x plus 1. And voila! This actually does work out. So our finite difference formula works out for a discrete variable x right here. But like I said, if you deal with differentials, we are dealing with continuous stuff. And that's what we are going to do next. So we are going to define basically our discrete summation right here over the real numbers, for example. So before I was having this little example with you guys about adding 3½ apples 3½ times to itself. And we left off there and we're going to continue from there. So what even does it mean to add 3½ apples 3½ times to itself? In arithmetic terms, you would write 3.5 times 3.5, okay? But what's 3½ something? Well, this is 3 plus 1/2. So let's go from there. That's nothing but, well, 3 plus 1/2 times 3.5. Okay, I'm going to put it like this. That's supposed to be a times right here, not an x, not a dot. Yeah, okay. But we know in the real numbers, for example, we have the distributive laws that actually hold, meaning we can distribute stuff into everything. So that's 3 times 3.5 plus 1/2 times 3.5. And here we go. Now it actually makes more sense. So what we are doing, we are adding our whole number x to our integer part. So the part of the number before our dot to it. So multiplying those together. And then we are adding our number x multiplied with our fractional part, the decimal places behind our dot right here. Okay. We can write this in more mathematical terms. What we get if we multiply x times x together, we are going to get, by this formula, well, yeah, we're going to put in more mathematical terms. Basically what this right here is the floor function of x. Okay, so we are rounding down to the nearest integer. If you have 2.95 and you use the floor on that, you are going to get 2, okay? Rounding down, floor function right here, times our x that we have, okay? Floor of x times x plus, and this right here, like I said, is the so-called fractional part, our decimal expansion, being denoted by those curly brackets. Fractional part of x times our x itself. If you want to be a bit more picky, you can actually rewrite this right here, this fractional part of x as well. If you think about this in general, what's the fractional part? Well, this is just our number x that we have, so 3.5, minus our rounded integer 3. So 3.5 minus 3 gives us the decimal expansion, 1/2 in this case. So we can actually rewrite this as the floor of x times x plus, okay, and like I said, this is nothing but our number x minus our floor function that we have times x. And well, if you straight through calculate this, you can use the distributive laws once again. You get this term and this term as the inverses from each other, the additive inverses, and you get x times x, which is nothing but x squared, and voila, yeah, exactly what we had in the beginning. Okay, this is cool. This is kind of our new addition being defined right here, but we can do better, because at first we had that x times x, x squared, is nothing but, if you have a discrete variable, sum running from k, from 1 to x in this case, of x, okay? And you see, this addition right here only makes sense if our x is element of natural numbers, for example. So if we have this right here, this floor function is always element of natural numbers. So we can actually take a look at this right here as being nothing but the sum running from k equals to 1 or n equals to 1 to the floor of x in this case, of x, okay? This is our sum notation just for this discrete part right here, plus the chunk that we had right here. X minus this chunk. Okay, this is basically it. We have defined our new addition in a cool little way using this right here. I'm not going to proceed from this part, I'm going to proceed from this part because we actually want to see if our rules right here hold. And for this we are just going to take a look at our, well, difference quotient and then taking the limit of the step size as the step size approaches 0. Okay, so that's something we are going to do now. So we know that ddx of x squared is going to evaluate to 2 times x. Okay, but we also want to check if this is equal to the limit, as I'm going to put h right here in normal case, I'm going to put delta x, but that's so much stuff to write, as h approaches 0, of, well, our f of x plus h minus f of x over h. What is our f of x? Well, we have defined it like this right here, okay? So this is basically nothing but I'm going to refer to this limit as just capital L, the limit as h approaches infinity of f of x plus h. I'm terribly sorry. So meaning we are going to plug x plus h into all of our x's right here. That's a lot of stuff to write. So that's the floor of x plus times x plus h, and then plus x plus h minus the floor of x plus h times s plus a, x plus h, oh that's so hard to say, x plus h, and then we are going to subtract our function itself from it, so negative, we are going to get floor of x times x minus the floor of x times x. And this whole thing, that's a long freaking fraction right here, over h. You can do the same spiel with this sum notation right here. It really doesn't change the output of the whole story, so yeah, that's cool. I want you guys to acknowledge something. Our h is strictly positive. We are going to approach 0 from the right. Let's put it like this, okay? Yeah, from the right. Our h is strictly positive all the time. And imagine our h is 1 at first. So we are going to get, for example, 4. 3 plus 1 is going to give us 4. But h is going to approach 0. Okay? So after a few iterations, we we have h, for example, being 0.5. So we get 3.5, and then we are going to get 3.2, 3.1, blah, blah, blah. So our h is going to get smaller and smaller. And the smaller it gets, the closer our floor of x plus h gets to the floor of x. The more our h goes to 0. Meaning, in the limit, basically, those floor functions are just going to be, well, the floor of x. So we have the floor of x times, and I'm going to write it out a bit, times x plus the floor of x times h plus, okay, this is, yeah, I'm going to put it like this, x plus h squared in this case, minus, okay, floor of x times x minus floor of x, like I said, floor of x plus h is going to the floor of x in the limit, times h minus floor of x times x minus x squared plus floor of x times x over h. okay, over h. That's a lot of stuff to write out. And now let's see if something actually cancels out. So we have those two being additive inverses from each other. So that's good. We have the floor of x times x, and we have this negative floor of x times x. Also we have this negative floor of x times x and this positive inverse right here, giving us, okay, now we have the limit as h approaches 0 of, okay, this is going to give us this binomial theorem is nothing but x squared plus 2 times x times h plus h squared minus x squared over, yeah, it's okay, over h. I'm terribly sorry. Okay, overall, yeah, I totally forgot x squared, and this x squared is going to cancel out. That's why I've written everything out. So this is going to cancel out. Also, we have this common factor of h, meaning in the derivative process, we're going to get rid of this h stuff right here, leaving us with the limit as h approaches 0 of, okay, this is nothing but 2 times x plus h. And now we can just use the rules of the limit to distribute those limits into everything. Well, this is just going to give us 0 in the limit, and the limit of a constant is just the constant itself, leaving us with 2 times x. Ta-da! Yeah, coolio. So now you know that this still works, but my reasoning was just absolutely disgusting because, well, I was treating this right here like it's a discrete variable, but I shit you not, when dealing with differentials, discrete stuff really doesn't make too much sense. Except you are defining yourself the finite difference like I did in the first example. I thank you guys for watching. If you did enjoy this video, please like and subscribe and recommend the channel if you like. If you want to support the channel a bit more, buy those t-shirts I create, or you can support General on Patreon. And well, up until next video, have a flammable day, I guess. Also, as a little information, in next time there's going to be a lot of integrals, a lot of analytical number theory stuff. So talking about the gamma function, the digamma function, polygamma functions, all this crazy cool stuff, Euler-Mascheroni constant, harmonic numbers, it's so fucking Gucci. So I hope you guys are excited for that. Love you guys, see ya.